All right, I think I'm on. So hi everyone. I hope you guys all know how much I miss you, how much I miss teaching in front of a class. It's very hard to be teaching to nobody in my living room, but I'm getting better at it. So hopefully this will go good. This is notes for section 2.3. We are going to be working on volumes of revolution, and this is called cylindrical shells. So the OpenStax book has really good images and good pictures. So that's what all of this is taken out of, is that OpenStax book. So if you want to look through that book and kind of follow along, you can, or if you can go back to it and use it as a references if you want to as well. So I'm just going to be kind of paraphrasing what they had in there. So kind of the same start off. This should look familiar to you. So this is the volume of just something underneath an equation. So this is y equals f of x. Could be quadratic equation, a cubic function, just any one of those types of equations this could be. And so you have your equation. Usually they're always cut off at y equals, at x equals 0 and y equals 0, both of those. And just looking at them in that first quadrant. Sometimes they start at 0, sometimes they start at 1. And then goes to a given amount of space. Okay, so with these, we are only going to be doing the ones that are rotated around the y-axis. Just because of time, they said we could cut out some things, and so I'm going to just do the ones that are rotated around that y-axis. All right, so when you take this shape here, rotated around the y-axis, you can see the kind of shape that we want to find the volume for. All right, so with our shell method, what I really kind of want you to think about, if you look at this last picture right here on the right, picture C, just kind of think of that as, well, really, it's like fruit by the foot. No, fruit by the foot, or what's the gum that like goes on forever and ever and ever, and you can pull it out. Anyway, whatever that kind of gum is, just kind of think of that. And so we're just going to peel off one layer of that. Actually, kind of like toilet paper too. But just like peel off one layer and think of that as a shell. That's what we mean by the shell method. It's just one layer of something that's been cut into multiple. Really, toilet paper is actually a really good example because the width of toilet paper is pretty much nothing, right? So that's really what we're going to do, is we're going to make this into shells. And what we can do with that, let's go down one more picture. All right, and so what we're going to do is we are going to take one full rotation of whatever that object is. Okay, so we're going to pull out one piece and we're going to cut it and roll it out so that it's a rectangle. So with that rectangle, and this is really kind of like if you go back to when we did nets, is what we called them. And so like if we did a cylinder and we wanted to know the surface area. So when we found the surface area of a cylinder, or like, let's say it was like the tuna can label, you wanted to know what that surface area is. Well, when you cut that label and pull it off and straighten it out, it becomes a rectangle. And this is really the exact same thing that we're going to be doing with the shell method, is we're just taking out one complete rotation of it, ironing it out so that it's the shape of a rectangle. And so now we want to know what that area is. And then we'll take that equation of area and we will multiply it by the width, which is going to be dx, or our delta x. See that right there? So since we are now actually, the width is still in terms of x. So that's what's really different. I want you to make sure you understand is that we are rotating around the y-axis, but we are going to be integrating in terms of x. Okay? So make sure you understand that width, the delta x, the width of each one of these pieces that we're going to take is our delta x, or our dx, because that's our differences in x is what we're actually doing. All right, so let's look at this shape right here. Okay, so think of back when we wanted to find surface area, how would we have found that area? Well, remember that the top we straightened out, that is really the circumference of the circle. So what's circumference? Well, either pi times diameter or 2 pi r. Okay? So, and where this, in this case right here, they're using x for the radius because x, the length of x, is really what the radius is. And we're going to have to take thousands of these shells or thousands of these strips to get the volume. That's why we have the change in x and why we're integrating in terms of x, because we want to find the sum of all of those different x values. But those x values are going to be what make up the radius, because every shell that we take is going to be a different radius. It's going to go out to whichever x value we're finding the area for. Okay, so that's where our delta x's all come into play. Now, so we would be integrating from 0 to whatever this outside number is. Okay, so we're not going to multiply it by 2 just because we're only taking half of it, because we only want to find the radius. The radius is in our equation. All right, so just because we're using the radius doesn't mean we're not finding the full volume. We are still finding the full volume because that takes that whole shape in. Okay, so 2 pi r is going to be the length of this rectangle, except for remember that r is represented by our x values. So 2 pi x is the length. Now the height is the height of the function, because that height is going to vary, right? It varies according to our function. Okay, so from x value up here, that's actually your y value of your function. So f of x, or whatever function they give you, is going to be your height. And then delta x is the width, which we want to be super tiny. And that's what an integral does for us. It finds us the sum of all of those. All right, so all of that brings us to the rule, the equation that we are going to use. So, cylindrical shells. The equation is volume equals the integral from a to b. And again, remember that's on your x-axis, and you can see that in this definition where it's giving you the definition. X equals a to x equals b. So we're always going to be going along the x-axis to find our limits of integration. So from a to b of 2 pi x. Remember, where did that 2 pi x come from? That should look familiar. That 2 pi x is the diameter of your cylinder, or the shell that we are taking, that one little piece of the cylinder. That is just the width, or the length, I guess I called it, of a rectangle, okay, or the diameter of our shell. And then f of x is the height. So to find the volume, we're integrating the area of one piece of our function. This is our length times our height, and then the dx is going to be the width of that. So when we integrate, the volume will come out of this equation. And so really, cylindrical shells is a really nice, easy method to do some of these more difficult equations. Okay, so what we have here is our first example, and we are going to be looking at the equation. So define R as the region bounded above by the graph of f of x equals 1 over x, and below by the x-axis over the interval from 1 to 3. So that's our limits of integration. And then you can see in here from 1 to 3 is where we're defined from, and that's on our x-axis. So find the volume of the solid of revolution formed by revolving R around the y-axis. Okay, so let's start off with just rewriting what that equation is. Where's my pen at? Oh, my tablet's asleep. Hold on. Okay, there we go. Okay, so our equation is, I'm going to write it up here at the top so I don't run out of room. Volume is equal to, I'm going to pull the 2 pi out because we do not need to integrate that. So 2 pi times the integral from a to b of x times f of x dx. All right, so remember this 2 pi x, this was the length of our cylindrical shell, and then f of x is the height. Okay, so let's go ahead and apply that to this problem. We've got the integral from 1 to 3. 2 pi we're going to put out in front times x times f of x. Now I got to go up here and find f of x. F of x is equal to 1 over x. So we're going to plug that 1 over x in, and we have our d of x. This is what our volume is going to equal. This is our equation. So let's simplify it a bit. So we have 2 pi from 1 to 3. Well, what happens to x over x? It really just becomes 1. And we could really even just write dx in there. You don't even have to write the 1. So now let's integrate. And we have 2 pi times the integral of 1 is going to be x. And we're integrating from 1 to 3. So we have 2 pi. I'm going to keep that out in front for a minute. I have 3 minus 1. When I go ahead and plug in, let's just say we're like that. Okay. So 3 minus 1 is going to be 2 times 2 pi. And 4 pi, and really we should be saying cubic units. So 4 pi cubic units is the volume of that object, and we're done. And that's really all that there is to it. It's really kind of a nice process. Alright, so let's go on to our next example. Okay, I got our second example pulled up here. So this one's really nothing any different at all. It shows us a really nice picture. We are finding the region bounded above by the graph of f of x equals 2x minus x squared, and below by the x-axis over the interval from 0 to 2. So again, they're giving us our limits of integration. Find the volume of the solid of revolution formed by revolving around the y-axis. Now I want to say really quick right here, if they did not give us those limits of integration, all I would need to do is figure out where that this equation that they give us, this equation right here, find where it crosses the x-axis. All right. So if they don't give you the limits of integration, find where it crosses the x-axis. Okay. So we've got volume equals 2 pi from a to b of x times f of x. This is our equation, dx. So for the second example, 2 pi from 0 to 2 of x times 2x minus x squared dx. And then we're going to simplify. 2 pi, 0 to 2, 2x squared minus x cubed dx. And now we can go ahead and integrate. So we've got x cubed, that'll be 2/3 x cubed minus 1/4 x to the 4th evaluated from 0 to 2. All right. And then we're going to have 2 pi. Also, on your homework when you're doing this, it is going to be asking for exact answers. So make sure you go through this and are finding the exact answers. 1/4 times 2 to the 4th. Okay, so that's supposed to say 2 cubed. 2 pi, and then we're going to have 2 cubed times 8 minus 1/4 times 16. And then going through all of that, I've got all my work written out over here. 4/6. Anyway, should end up with that equaling to 8/3 pi. Yeah, because that's 4.